Hello, guys. So you are welcome to this lecture. So in the previous lectures, we looked at vector spaces, we defined it, and then we did some examples to show how to prove that something, a structure, right, is a vector space or a set is a vector space, and how to show that a given set is not a vector space, okay? So here we want to prove a very simple theorem under vector spaces. That will basically be this lecture. And then the one to follow will be subspaces, which I will do later on. Okay. So here's your theorem we want to prove. Let V here be a vector space. And let U here be an element of V and lambda be a scalar. Then if I take 0 multiplied by the vector U, I get a 0 vector. Okay. Remember, this 0 is different from that 0. This 0 here is a scalar, okay, from your field. And U here is a vector from V, and 0 is the 0 vector. Okay. If I take a scalar lambda multiplied by the 0 vector, I get 0. If I take -1 times U, I get -U. And the fourth one, so very important, if I take a scalar times U and I get 0, then either lambda is 0 or U is 0, okay? Remember that when we're dealing with fields, okay, rings and fields, we come across the fact that it's possible to multiply two elements to get 0, even though neither of them is 0, right? In this case, we said that, you know, if that happens, then either A or B, they are said to be 0 divisors. So in this case, we don't have 0 divisors under vector spaces, okay? So if you multiply a scalar by a vector and get 0, either the scalar is 0 or the vector is a 0 vector. That is what it says. So we'll prove this. We're going to prove this this theorem. It's quite straightforward, actually. They look actually very basic, but you still need to prove them. Okay. So let V be a vector space. So that is given to us. And let U be in V and lambda be a scalar. Well, if I multiply 0 by U, I can rewrite it as this. 0 is the same as 0 plus 0, right? So this is fine. I can use the distributive laws under vector spaces, right, to rewrite this as 0 times U plus 0 times U, okay? Good. So we have this result. We'll use this later on. Now, if I have 0 times U, obviously, this is an element in V. This should have an additive inverse, right? V is an abelian group, so it has an additive inverse. So this guy plus its additive inverse should give me the 0 vector. So this is obvious from that. But 0 times U here is the same as 0U plus 0U. So I can rewrite this as 0U plus 0U plus this guy. I can apply associativity, again, because V is a vector space, it's an abelian group. So associativity holds an addition. So I can rewrite this using that. But this is an element plus its additive inverse. So that should give me 0, right? So this plus this is 0. 0 is the identity. So 0 plus OU should give me 0U. So 0U is actually equal to 0. So that is clear. Okay. In fact, from here, it appears obvious, right? Because 0U is equal to 0U plus 0U. All right. Basically means that if I take 0U plus some elements, I get back the 0U. So that element has to be the identity, which is 0. So here 0U has to be 0. Right? Okay. So, but we have proved it in a more. Okay. So that is that. The second one is we want to show that if I take a scalar multiplied by 0 vector, I get a 0 vector. Okay. So let's prove that. It's going to be similar to the first one. So I take lambda times 0. Again, 0 can be written as 0 plus 0. And I distribute it, right, using the distributive property of vector spaces. Can write this as lambda times 0 plus lambda times 0. Okay, good. Again, if I take lambda times 0 plus the additive inverse of that, all right, I can rewrite lambda times 0 is the same as this. So I can replace this guy by that. So I have lambda plus the inverse of this, which is this, okay? Again, apply associativity, and I can rewrite it as this, right? On the left-hand side, this and this is 0 because this is the additive inverse of that, so that's fine. So on the right-hand side, I apply associativity. Again, this plus that will give me 0 because that is the additive inverse. So I have lambda 0 plus 0. Well, it's the identity. So if I add it to this, I get back lambda 0. So lambda 0 has to be equal to 0. So that is what we have here. Okay. So we have proved the second one. The third one is to show that -1 times u is equal to -u, right? So we want to prove this. Okay. So we start with the fact that -u plus, well, we want to prove that -u plus u is 0, and therefore -u times u is equal to -u. That's what we want to do. Okay. Similar to similar one we did when we're dealing with, I think, rings also. So you have -1 times u plus u is equal to -1 times u plus. Remember that one of the properties of vector spaces is that if I multiply 1 times u, I should get u, right? So u is the same as 1 times u. Okay. Again, I can use the distributive law, right, to pull out u, and I have -1 plus 1 times u. Okay. But -1 plus 1 will give me 0 because 1 is the additive inverse of the other. So that's giving 0, 0 scalar, right? Multiplied by u. But we have just shown that 0 times u here will give me the 0 vector. Okay. So what that means is that -1 times u plus u here gives you 0. 0 is the identity. Therefore, right? Therefore, the additive inverse of this guy here is a minus u, right? Or this is equal to -u, which is this. So this is what we wanted to show. All right. Okay, good. So we are left with the last one, which is more interesting, I think, here. So we want to do it by contradiction, right? Here, this says if lambda times u is 0, then either lambda is 0 or u is 0. So what we're going to do is that we're going to assume that neither lambda nor u is 0, and yet their product is 0, and show that that contradicts our assumption, and therefore one of them must be 0. Okay, that is the plan for that. Okay, so this is given, right? So now we are going to suppose that this product is 0, right? And then assume that lambda is not 0 and u is not 0 either. Okay, if that is the case, then of course I can write u is equal to 1 times u. Okay, 1 can be written as 1 over lambda times lambda. Lambda is not 0, so I can write 1 over lambda here, right? Okay, and 1 over lambda times lambda, of course, gives me 1. So that is 1 here. Good. Now I can use associativity to rewrite this, right? This, not associativity per se, right? Associativity in terms of the scalars. Remember, one of the axioms of vector spaces, you have lambda and mu multiplied by the vector, right? You can regroup them. So I can rewrite this as 1 over lambda multiplied by lambda u, okay? But look here, this guy. If you look here, we said lambda u is equal to 0, right? And so this becomes 0. So I'm going to have 1 over lambda times 0. So I have a scalar multiplied by 0, and that should give me 0, right? But look at this. We assume that u is not equal to 0, but this analysis is telling us that u is equal to 0. You see? So this contradicts the assumption that u is not equal to 0, and hence either lambda has to be 0 or u has to be 0. Okay, and that proves it. Okay, so if you have under vector spaces, if you have a scalar multiplied by a vector and you get a 0 vector, either the lambda is 0 or the u has to be 0. You can't have both of them non-zero and yet you get a 0. Okay, good. So that is the end of this short lecture. The next one will start off with subspaces. Okay, we'll look at subspaces in our next video, next lecture. All right.